It's a great pleasure to welcome Vlatko Vedral, and I see it's a very interesting title, that whether there are any fundamental problems at all with quantum gravity. Okay, let's hear Vlatko. Yeah.
Thank you very much, Sugato. It's a pleasure to speak here. We had some fantastic talks this morning, actually, and this is all about to change now. I will go into a kind of denial mode, as Sugato said, in the sense that I will use this method of raising a problem and saying that it's not a problem, just to be maybe a bit more controversial, and I think to suit the dialogue style of this meeting. So I just want to take you through a sequence of things. I changed from the original title because I thought this was more appropriate. I will comment on the thing that I intended to comment on originally. So hopefully that will be there too. So I want to tell you that things like entanglement, equivalence principle, they are not really a problem, conceptually speaking, of course. Field on itself problem, I don't think that presents a particular problem for quantum gravity. People talk about all sorts of non-local observables, gauges, diffeomorphisms. I think they're frequently raised again as fundamental issues, but I don't think they are at all. You know, then people talk about time problem, measurement problem, and I don't think these are really problems. Frequently, I think these problems occur depending on the background of people who write about these things. And that's something that I will try to emphasize. And then, of course, there are these nonlinearities that, you know, people informally say gravity gravitates. Again, at the level that we are discussing, these really are no different to any other field theories. So I think I'm going to be taking this kind of phenomenological perspective that anyway field theory in its own right is probably just an approximate way of dealing with things at the most fundamental level. And I think gravity is not really a particular exception to anything else. That's kind of what I would like to communicate at this level. So now, entanglement is a very simple misunderstanding. And I think you will see a lot of literature here where people say, well, entanglement is a kind of non-locality. And, you know, gravity is classically is a field theory. It's meant to be local. And if this really was an issue, then, of course, this would be an issue for any field theory. But we know that entanglement is an intrinsic property of quantum fields. It's not that it's in contradiction with anything. And I think this slide simply wants to say that this is a terminology problem. That when we talk about non-locality in quantum physics, what we mean is frequently Bell non-locality. So that means that if you're faced with the choice of keeping the classical reality, meaning that everything is underpinned by some kind of numbers, then you're gonna run into problem with locality. So the choice is always losing either the locality or losing reality. And I think all of you familiar with Bell's inequalities will immediately recognize all of this. Now, I would say the way that we've dealt with this, and I think most people will agree with me on this statement, is that the underlying reality is, of course, not classical number reality, but the underlying reality are quantum numbers. They are observables. They are non-commuting quantities. As soon as you acknowledge that, you realize that everything is nice and local. Quantum field theory is as local as any other field theory. It's just that your elements of reality, of course, are not classical beables, as Bell would say, but they're simply Q numbers. So there are no issues there. There are a few slides that I'm probably just going to skip over, but people usually talk about an interferometer where you kick in a phase in one arm of the interferometer. And then people say, look, if I have a particle in one arm superposed with the other arm, and I kick a phase in one arm, then it looks, mathematically speaking, as though the phase could have been kicked in the other arm. And many people would call this non-locality of quantum wave function, but I think this is complete nonsense. This is just this is a remnant of using first quantized language when actually you shouldn't be using it at all when you're talking about quantum field theory. So somehow this Schrödinger way of calculating things frequently misleads us into believing that when you kick in a phase in the upper arm, that looks automatically as though the phase is kicked into the lower arm of the interferometer, and you know, it's a simple artifact of the Schrödinger picture. And of course, all I'm emphasizing here, and it's a very nice instructive calculation, is that if you did everything in the Heisenberg picture as a field theorist would do, if you associate, if you're thinking of a photon now, but you can do this calculation with any particle, you have the electric field in the left hand arm, in the right hand arm, then you kick in a phase, and you can see in the Heisenberg picture that the phase only enters on the left in one arm. It's not present in the other arm. It's completely local, like any other field theory. Then you do kind of the final beam splitter. And what you notice, of course, is that
you can see
you've done the usual calculation, but in the Heisenberg picture, and it's only at the final second beam splitter that your phase that was kicked in one
so
arm
good morning,
is now
good afternoon,
present,
good evening, everyone, wherever you might be,
in both of the
thank you
output arms of your interferometer, and it gives this usual cos squared and sine squared pattern. So quantum mechanics, I want to say, is in the relativistic sense as local as any other field theory, and entanglement is simply just an aspect of that. There is nothing non-local about it, and I
7
urge
o'clock
people to stop.
Here on the West Coast, the sun is creaking over the horizon.
Now, what I'm going to say, and as I go along, it may become more and more controversial, and I hope it does. You know, that's exactly
7
what we're
o'clock
hoping to discuss.
here on the West Coast, the sun is creaking over the horizon, and we have a very
into quantum has to be imported carefully.
I've been taking is to try to leverage all of this theoretical progress, mainstream theoretical progress.
There are superpositions and so on, so we have to be careful with that. But something that Yair mentioned earlier
as a
was
causal
the equivalence
diamond,
principle,
which
and
of
this
course
is
it is.
frequently brought
I
as
have
being in
a signal beam and a reference
some
beam.
kind of conflict
Throughout
with,
this talk, I'm only going to be
with
talking
quantum
about
physics. And I
length
want to say again
fluctuations
that
in
this is
one
not true
beam.
at all.
As time goes on and we get better control over the theory, we'll be able to more
condensing it
precisely
into 2
correlate
minutes.
these. I'll talk
But
about
basically,
later on
very loosely speaking, acceleration and gravity are locally indistinguishable, and that's the equivalence principle. And now what people ask is, what happens when I have a massive object that gravitates, but it's in a superposition of 2 different locations? And that's, of course, the key topic for this meeting. And the answer is, again, very simple. This is true for any classical symmetry, be it a conservation law of any kind, and I'm thinking of the equivalence principle in no different way. So as soon as you encounter quantum mechanics, you encounter something that Bryce DeWitt, I've learned this from David Deutsch, called quantum totalitarianism, which simply means that anything that couples to a quantum superposition must become entangled to it. I mean, this is, of course, Schrödinger all over again. And all of the experiments that we keep discussing, as we know, are really just more or less complicated variants of the Schrödinger's cat experiment. There is no other experiment really out there in quantum mechanics. They're all the experiments of this kind. And so what happens, and this is an artist's impression of a massive object here, if you can see my cursor, basically in a superposition of 2 different places, and you have a test mass down there, and the question is, how is it going to respond? And if you stick dogmatically to the classical principle of equivalence, you're going to have to say, and this is what various collapse theories believe, that this test mass will accelerate either towards one of these locations or towards the other one, but it will have to be one or the other. And what I'm saying is a simple statement that this is a mistaken view, simply because when you have a superposition quantum mechanically, then both of these options happen simultaneously. So basically, your test mass will accelerate simultaneously towards one of these locations and towards the other one. And this will really give you an entangled state. I think this is very similar to what Sugato and his colleagues and Chiara and myself have been describing, that actually you will create, of course, a superposition of these alternatives, and there's absolutely no conflict there. That's exactly what quantum mechanics suggests. So I'm summarizing here that totalitarianism simply says, just like the Schrödinger cat experiment, that anything that interacts with the superposition must simply join in this entangled state. Of course, I'm talking in terms of principles here. I'm not talking about how long this entanglement will last, whether it will decohere due to other effects and all sorts of other things that are, of course, very important for our discussions. Let me go through a few more of these denials that I have on my list. You frequently hear people say, oh, gravity is different because it's a field on itself. Again, I'm using a very loose language here. What I mean by that is that when you specify a quantum field, you specify an operator at a point in space and an instance in time. But now the space-time itself is like a field. So I'm kind of writing it very badly. I think a mathematician would probably draw a gun now and shoot me on the spot. But what I'm writing is G mu nu as an operator, as a function of itself, G mu nu. And the question that some people get tangled with is, what does this mean? I want to warn you again that if space-time ought to be quantized, then this is an issue for any field theory. It's nothing necessarily trickier for gravity than anything else. And of course, there are many interesting issues there, but I believe the problems that we are discussing at this level are very, very far away from questions of this kind. And questions of this kind may well lead us to go ultimately beyond quantum field theory, but I don't think they are per se an issue for quantum gravity at the lab level that we are discussing. Another typical thing that you'll be hearing is about quantum references. So lots of these complaints come from people who haven't fully quantized themselves, as it were, just to put it again in a colorful language. So what they haven't understood, and it seems to me even many field theorists don't understand that when you're trying to impose a symmetry, when you say, let me write down the state from the perspective of one observer, and then let me do a unitary transformation, as Wigner said, to encode it as though it would be seen by a different observer, what should immediately occur to you is that this is not just either or situation, but it can always be in a superposition. So as soon as you can have a stationary observer, an observer that undergoes a boost, quantum physics automatically says you can make a superposition of these two. And this is again part of quantum totalitarianism, and there is nothing contradictory about this. This is just beautifully captured by taking quantum mechanics at the macroscopic level and simply quantizing everything. And I have this phrase that I picked up from Tony Sudbury. I think he attributes it to me, but I think he's mistaken, that unobserved outcomes can actually affect future measurements. So I think these lots of mistakes that come from people who claim that the measurement problem will be problem when we quantize gravity just simply come from the fact that some people think of measurements in the old classical sense, that when you observe an outcome, it's once and for all, and it's true for everyone in the universe, for all observers. And this simply is not correct. If everything is to be quantum, which is kind of the picture we are trying to test, then different observers, of course, may see different things. You can possibly do Hadamard gates on the memory of the observer. You can play with observer's memory, go into complementary states, and all sorts of things like that are possible. And there simply isn't any contradiction there at all. I have all sorts of slides that I kind of took from popular talks. I only want to actually tell you about maybe the papers where I've written about these things. I don't want to bore you too much. And of course, if there are any questions about this, I'm happy to answer them. None of my papers, when I'm a single author, are going to be in journals. I can't be bothered to publish anymore. I think archive is good enough. And I think hopefully other people will go in that direction as well. Anyhow, so nested observers, observing observers are all possible within this. In fact, the message of macroscopic quantum mechanics is that there is no difference between the observers and the observed, and this is all perfectly consistent with quantum mechanics. Now let me spend a few more seconds on one or two more problems, and then I will say something possibly more positive. Another is the problem of time. This again is not a problem of quantum gravity in my view. Time can be reparametrized. It's a standard trick in classical physics as well, which is at the root of many of things we do also in quantum gravity. What I'm talking about is this timeless view of Page and Wouters, which some people say suits the kind of GR block universe more. But I just want to alert people to the fact that this is a simple reparametrization of time. And this is a trick that you can play with classical Hamiltonian dynamics, reaching very similar conclusions to quantum mechanics, actually. So I don't think time presents us with anything different than what time really presents us in the classical context. Now, the twist quantum mechanically, like I said, is that we can have superposition of different times. And this already occurs in special relativity. You can take a particle that simply travels in a superposition of two different velocities. You can do a twin paradox, relativistically speaking, with a single particle. You can then interfere these two times. All of this has well-defined calculable effects in quantum mechanics, and there are absolutely no contradictions there. I actually, when I say all of these things, I sound very frustrated because I myself would love something to go wrong at this level, but it seems to me that my bets are really on quantum mechanics being perfectly satisfied at this lowest level of approximation. So let me now move on to the real problems, which are really to do tests. I think what we are really missing is good experiments. And as we heard from this morning's speakers, this is an exceedingly difficult thing to do, even in the non-relativistic Newtonian gravity, but of course at the interface with quantum superpositions. So this famous cube where you have Newton's gravitational constant, the speed of light, and h bar signifying three different regimes. Of course, the theory of everything here is at one corner where all of these constants become important. But what we are really doing, we are barely scratching the surface at this corner here, where, as Marcus mentioned, experiments like his own or Kao experiments, Yair's experiment too, are all the experiments that are somehow combining classical gravitational effects with quantum superpositions. But what I want to say is that even Newtonian gravity, thought of as a field theory, would be somewhat in this semi-classical regime, because we're not even yet necessarily talking about genuine quantum gravity, or we are talking, let's say, about the lowest order approximation to these effects. So we are really hovering above this vertex here and trying to get as much out of it as possible. And it's really very, very questionable how long it would take us really to get to the regime where G and H bar somehow and C equally matter. And of course, we all know why this is. I think this has been repeated many times, that the gravity is a very weak interaction. I mean, this is just to tell you about coupling of matter to the gravitational field. This is the fine structure constant that tells you how strongly atoms, let's say, will couple to the electromagnetic field. Let's say it determines the rate of spontaneous emission. The corresponding gravitational fine structure constant. So if you excited an atom and you waited for this atom to emit a graviton instead of a photon, you're never going to get there. Of course, this will be many, many orders of magnitude longer than the age of the universe. So that's something we are facing. The question is, can we, despite of the weakness of gravity, still say something interesting? And of course, I think we can, and many other people agree with me on this aspect.
You have 5 minutes.
Thank you very much. I'm literally going to make possibly one more comment, and then I'm going to stop. So because you would have heard a lot about Sugato's proposal and Chiara's and mine and many other related proposals, I'm not going to say anything about it other than the emphasis that it seems to me that a single massive superposition is not enough to conclusively say anything about the quantum nature of gravity. It would be enough if, of course, we make extra assumptions of various kinds. But if you really want to have something that's more conclusive and depends as little as possible on the underlying theories, then it seems to me we're going to have to go down the road of two massive particles interfering, each of them interfering, and then somehow getting entangled through the gravitational field. And again, I don't want to go through this, but what I want to now stress is this single massive superposition. So if you put a single mass in superposed state of two locations, let's say, then if you even manage to get quantum interference, the problem is that this really doesn't tell you anything about the surrounding gravitational field. And what I have in mind here is that if your mass interferes, it could simply be that the surrounding gravity is classical, or it could be that it's quantum, but it basically entangles to the mass in a way that it causes what we call fake or false decoherence. This is something that people like Andrew and Tony Leggett would have written a lot about, which means that your mass gets entangled to the gravitational field as you create the superposition, but as you bring it back, your mass disentangles from the field, and therefore it is perfectly possible that gravity is quantum mechanical, but it does not lead to decoherence. So being able to interfere a single mass tells you absolutely nothing. Now, the counter of this statement also tells you nothing, and that's the problem with having only a single mass. If you're not able to interfere a single mass, then you cannot also conclude anything about the gravity, even if you know, by the way, it couples only to gravity. I'm not even going to talk about other problems that could occur there. And the reason is simply here that gravity could still be classical, and it could cause collapse of interference. This would simply be some kind of classical dephasing. And there are people who believe that it's possible to have only classical dephasing. I don't believe in it. As I said, I'm into the totalitarianism of quantum mechanics, but I think it's possible that it's only classical. And then, of course, it can even be that you not being able to interfere a single mass is a proof of the quantum nature of the gravitational field, because the field now, by entangling itself to the mass, simply decoheres it. So, you know, at the level of a single mass, these experiments, even though they could be impressive if you achieve interference there, they're not really going to conclusively tell us anything about the gravitational field. So somehow we really must go in the direction of minimum two interfering masses. And I think this slide is really just to alert you to the entanglement that's created between the mass and the gravity. But what I really want to comment on is that this doesn't mean, of course, that it's not worth doing single mass experiments. It just means that the conclusions that you have reached are going to be heavily colored by the kind of theory you're going to be testing. So these experiments are more like metrology type experiments than probing and discriminating collapse versus quantum gravity and so on. And here I'm citing a couple of papers, and I think you will hear at this meeting a lot more about them as well in the next few days. Maybe the final comment, because I know that people raise this objection very frequently, is that the Newtonian phase is instantaneous, some people say. At that level, you're not testing quantum nature of gravity when you entangle two superpositions. But I think this is simply a mistaken view from really taking the Newtonian version of gravity, which of course itself was instantaneous. However, if you treat this as a field in the lowest approximation of GR, you will of course get that Newtonian gravity propagates at the speed of light the same way that any other field would suggest. So if you have two masses and you move one of them, it will take a finite time. The propagation will be at the speed of light. Of course, these are your gravitational waves. And so the explanation here is just as causal as any other explanation, which is why this is actually a good test of the quantum degrees of the gravitational field. I'm going to literally put the conclusions here and just go through them very quickly, but it summarizes the view that I've been promoting here, that gravity is not a priori incompatible with quantum mechanics, no more incompatible than the problems we are facing in quantum field theory. We have to get used to this fact that our fields are now really quantum numbers. They don't commute. We have to use that. If we stick to classical numbers, we, of course, will run into trouble with locality. The good news is that quantum effects can, in principle, be tested. I think that's really encouraging. We've heard that these experiments are extremely challenging, but it seems to me there is a number of optimistic people at this meeting, but also other people that I've talked to who believe that this is actually doable. And this last comment, that I think whether gravity is normalizable or not, it seems to me to be completely irrelevant for what we are discussing. I think if you take the phenomenological view of gravity and of other fields, then I think this really is just not a problem at all. What we really do need is to work on experiments to test even this lowest order regime. And it seems to me that's where the focus really ought to be. Thank you very much for your attention.
Okay. So thank you very much, Vlatko. And I'm sure this would have provoked a lot of questions now. So yeah, if there are some comments people would like to make. If nothing is immediately forthcoming, maybe I just maybe Nancy has something to ask.
Yeah, I guess if no one else, I was just wondering on that cube of H bar G and C, how do you put in perspective probing different regimes when you're going to higher masses or lower masses? Where do we put that kind of information on that representation?
It's a good question, actually. So somehow when I was going in this direction of theory of everything, people always talk about very strong gravity, as well as quantum mechanics. So of course, the first thing that comes to mind are massive objects like neutron star or black holes, where possibly both quantum and gravity have to be taken equally seriously. Unfortunately, again, all we have are really semi-classical predictions. Things like the Unruh effect and maybe Hawking effect are really treating space-time as a background. They're not really quantizing gravity at all. So it's possible that in that regime, we may have to do something genuinely quantum gravitational, but I don't think anyone has any good ideas. So that's kind of how I envisage moving, as you said, between this corner towards the kind of corner where everything becomes important.
Yeah.
Yeah, so maybe Dan wants to say something.
Yeah, sorry to clog the airwaves since I'm going to talk in a minute, but so I really enjoyed this talk, and I really agree conceptually with everything. Just to Nancy's question, I mean, and it's related, I mean, there are problems, but they only appear the far ultraviolet. And that's sort of the thing that's not said in this talk. So when the curvature is very large, then the curvature and curvature nonlinearity is important, and that's when all the deep stuff happens. So that's not going to come, you can't actually probe that in a direct way by just making a heavy mass. You need a heavy energy density, right? Yes. And so that's really what you want to do to get to that corner.
Yes, I'd love to talk to colleagues in astrophysics, because it seems to me there is an awful, certainly I am complete dilettante there, but it seems to me that maybe some astro and cosmological things could be utilized to already draw some conclusions there.
So If I may, let us then thank Vlatko, and I know there are a couple of more questions by Nick and Marcus. So should maybe we just wait for them to get the first questions in the discussion time. Thanks, Vlatko.
Thank you.
And yeah, so let us start with Anupam's talk now. So yeah, Anupam, if you would like to share and start.
Thanks, Sugato. So being an organizer, I'm also giving a talk, and a part of the reason is there's a huge misconception in the community, and I thought I would try to present slightly different viewpoint, partly because the field I come from particle physics and gravity. So my desires are slightly lesser than many of my colleagues here. So I'm going to talk about witnessing quantum gravity in a lab, of course, but the desire is less because I have a slightly lesser degree of question. I want to understand. So yeah, it is wonderful that we want to understand whether gravity is quantum or not. But I want to bring it down to slightly more at a microscopic level and say that whether graviton is quantum or not. And these are the papers which I will be talking about. And as you can see that you have a Cheshire's grin, and if you look into the grin, you see the graviton structure here. So let me make a plan for the talk. I'll discuss quite heavily on graviton properties, and I'll tell you that why it is important. Then I'll talk about classical versus quantum divide. And then I'll talk about this protocol, which many times now we have seen it, including Vlatko's talk and Sugato's talk and also Carlo's talk. The challenges, they are humongous. We are somewhere here. Imagine that we have to climb Mount Everest, and we are novice. And what we would like to do is that we would like to test graviton, not in a LHC kind of machine, not in a cosmic colliders, but in a very tiny laboratory, roughly around micrometer, the kind of like chips which a couple of minutes ago, or hour ago, Yair was talking about. So what is gravitation? So let me present you a sestet. So actually Newton assumed it. He did not ask the question that what caused that force. He simply assumed it, and he was a fantastic phenomenologist. He fit the data very well. It was the Hooke who was trying slightly harder to understand it. And what initiated the entire thing was, after all, the Maxwell. It was the Maxwell's equation, although in a different context, not in the context of gravity, but electromagnetism. He initiated the entire framework of field. And then Einstein framed it in the context of gravity. Feynman, it took some time to Feynman, like Genius and Feynman, Schwinger and Tominaga and many other contributors at the time to understand it, to solve it in a formal language. And now the question comes is that how do we falsify it? So what mediates the force? And this is what we are trying to falsify it. Let's go back one couple of steps back. Let's go back to the quantum mechanics and how quantum mechanics goes into quantum field theory. Quantum field theory is based on quantum mechanics. Quantum field theory does not throw away quantum mechanics, exactly like Einstein's theory does not throw away Newton's potential or Newton's laws. It recovers in a limit. So as you know, in quantum mechanics, you sum over all possible paths when you go from A to B. The same thing happens in the case of field, except that now you have infinitely many harmonic oscillator. With the help of Dirac's trick, you can write down this sum over all possible paths in terms of Lagrangian. And the same thing happens in the case of field. One of the quantity which is very important in fields is that going from vacuum to vacuum transition. And now you can describe it not in terms of paths, but in terms of field. Now the field could be spin 0, spin half, spin 1, 3/2, 2, or even higher spins. String theorists talk about higher spins. So you can talk any spins, and you can take any spins and discuss physics now. What is important is as soon as you keep some object, some conserved quantity, it could be conserved current, it could be conserved energy momentum tensor. As soon as you place that, you disturb the field because you're coupled. You're not in the universe, you're never in a situation where you're uncoupled. You're always in a coupled system. You're interacting with some other interaction, let it be QED or QCD or gravity, as a matter of fact. And the quantity which you are interested in this transition, essentially want to understand what's the transition probability going from initial state to your final state. So in this particular case, you have got Alice and Bob, both have conserved current. The Noether's conserved laws comes into the game, and what is mediated is nothing but the propagator between the Alice and Bob if both have the two conserved currents. So what are the properties of a propagator? Propagator in field theory is time-ordered causal Feynman propagator we are talking about. It's non-instantaneous, as it has been highlighted many times now. It doesn't satisfy the classical equations of motion, and it's well within your uncertainty time relationship. And everything is happening within your causal patch. Nothing goes beyond the causal patch. So just to give a parallel between what is photon and graviton, and this has been discussed several times. So what you usually, when you quantize, say, photon, what you quantize is the degrees of freedom. And that's the place where you have to be a bit more careful what degrees of freedom you're quantizing. You can also quantize even the dead man or a dead woman, because you quantize in field theory ghosts as well. So what happens is that you have to ask the relevant degrees of freedom you want to quantize in order to understand the subtlety or understand the physics carefully. So in the case of photon, if you look into the on-shell photon, the degrees of freedom, you can do various maths, various different ways. It's the 2 degrees of freedom which you're quantizing. The same thing happens for a graviton. The plane wave graviton, the on-shell graviton has 2 degrees of freedom. These are your famous H plus and H cross, the 2 polarization states of graviton. In the case of electromagnetism, you have a dipole. You shake the dipole, you get photon. In here, in the case, you need a quadrupole moment in order to create these gravitational waves. But when you place things in presence of matter, so in presence of matter, you need to talk about this propagator. In the case of photon, the degrees of freedom increases. It becomes the propagator. What propagates is this covariant propagator, which is sandwiched between the 2 conserved currents, J1 mu and J2 mu. And the total degrees of freedom are your 3 degrees of freedom, the transverse photon component. In the case of graviton, again, you have got 2 conserved energy momentum tensor, because you're talking about this rank 2 field. Is the energy momentum tensor which enters, and this is the propagator. Again, if you want to understand in the scattering diagram, in the S matrix formalism, going from initial state to final state, you are sandwiching your propagator between 2 conserved energy momentum tensor. And if you look at this quantity, that's your propagator, where you have spin 2 degree of freedom and spin 0 degree of freedom, which propagates, total 6 degrees of freedom, which propagates. And this is effectively your graviton, which contains not only the transverse component, but also the scalar component. And this is what essentially people quantize in the context of cosmology, because they talk about perturbations in your metric, as well as in presence of matter, the scalar fluctuation, which gives you the CMB, cosmic microwave background radiation, and the tensor perturbations. So imagine this is your scattering diagram. So you're bringing in 2 particles, exactly like your proton-proton beam. In LHC, you are bringing 2 masses close to each other. You can perform this calculation in relativistic formalism, and you can write it down in terms of Mandelstam variable. S, T, U are your Mandelstam variable. And from here, you can go to the non-relativistic limit. And when you go to the non-relativistic limit, you get this GM square over R. So here again, you have to keep in mind that what entered here is your propagator, which has both the transverse traceless graviton and the scalar component. So physics hides actually in this propagator. You can change the physics of gravity, and you can change the degrees of freedom for a massive gravity, for other choice of gravity, things will be different. So let me give you just in general relativity. Now we know all our higher order terms. I have written ... but our colleagues from Donahue and other colleagues have computed perturbatively even, and especially it's very much important for post-Newtonian corrections in LIGO. People know various post-Newtonian corrections for a static source, for a rotating source. And many times I have noticed that in the community, people make huge mistakes and there are wrong papers written. I don't want to point anyone, but first thing first is the H-bar correction. The way it appears with G square factor. So that's something which is very important. And sometimes you would find certain people trying to recover the H-bar correction even at this level or even at this level. And those papers are absolutely not correct. Similar thing happens even for rotating source. The H-bar correction comes with the G square and further separation is 1 over R5. That makes detecting these kind of terms in experiment in a laboratory extremely, extremely hard. So these are very well-known computations. Many groups have computed very accurately. These are well-known machinery. And as I said, that you can modify your gravity, this provides you also an opportunity. Suppose, how do you know whether graviton has mass or massless? You can test some of these hypotheses now, because we have not tested gravity at very short distances. When we put the mass of the graviton, we put the limit on very large scales from LIGO, but not at very tiny distances. So depending on the nature of how you modify your gravity, you modify your propagator, you add extra contribution on your general relativity propagator, you get different kind of potential, and you can test your theory this way. So just to give a very outlandish example, if you want to test even non-locality or non-local interactions, even field theory, that you can even test because you get different modifications because of the modifications in your propagator. So I'm not going to the details, but just to let you, for further discussion, these are the relevant topics which I think in future one can probe. Now, so challenges for detecting graviton. Detecting a graviton itself is a huge challenge, and we know that from the days of Dyson, and before Dyson also people knew that it's not going to be so easy. The reason is, again, it has been highlighted by many people now that the coupling is very tiny. This is your interaction. This is your h mu nu, tiny little perturbation in your space-time around Minkowski background. You're not changing your light cone, you're perturbing around Minkowski space-time with a very tiny perturbation, which is a h mu nu times t mu nu. Now, if you look into this interaction, and if you go into the non-relativistic limit, let's say that you want to treat your h mu nu as a quantum, as well as t mu nu is quantum, and you want to understand by taking both the theories at a quantum level, at the perturbative quantum level. So you're not going to the non-perturbative level. In the perturbative quantum level, you are taking both the matter sector as well as the graviton at the same footing. But if you want to trace out the matter component, suppose you trace out, so you have got a system with its gravity and matter, and that's it, and you want to trace out the entire matter degrees of freedom, then what you get is essentially, very interestingly, this is a remnant of this fact, actually. The fact that I was talking about, this is your graviton, so the transverse component has this component as well. But when you essentially trace out all the matter degrees of freedom, what you get is a displaced coherent state for gravity. And when you look into that, for the displaced coherent state, you can associate number and essentially occupation number, and occupation number of graviton in this context goes interestingly by this quantity gm squared. And if you look into this fluctuation, it goes as 1 over square root of ng. For a very large number of gravitons, so the way you get large number of gravitons, if your mass is very heavy, effectively you get large number of gravitons. So effectively what it means is fluctuations is very tiny. So this can be treated as a divide between classical and quantum, and under what circumstances I can perform certain experiment. Surprisingly, this quantity is nothing but the area over G, the Bekenstein's entropy, which Bekenstein found way back in 1983. So it's a slightly different way of approaching the problem. We are just tracing out the matter and just looking into the graviton, and what we find is that this famous Bekenstein's entropy arises. Now, just to give you some example, if you take mass to be 10 raised to minus 5 grams, you find the number of gravitons roughly order 1 in the system. So what it means is that if you create a mass which is 10 raised to minus 5 grams, effectively you have or order 1 number of gravitons sitting in your system, close to a Schwarzschild radius. For every system, you have a Schwarzschild radius, and the fluctuations is given, as I said. So for a very heavy system like astrophysical black holes, effectively, these astrophysical black holes are effectively a classical system. And this is not my, my point of view. This has been advocated by many people, by Gyadwali, and it goes back from the days of Wheeler even, who has advocated this point that, these are the fact that astrophysical black holes, which we see, they have classicalized. So gravity has become classical system for a very, very massive system. So for such a system, extracting quantum properties is also very hard, and that we have seen it. The Hawking radiation, that's the only way you can extract. But Hawking radiation is so tiny, that it's hard to even detect it. We will perhaps never detect any Hawking radiation from any astrophysical black hole. So our best bet is to go for system with a lower mass. Now, if you look into the cross section for the gravity, and let's say graviton interacts with proton or electron, even that is very tiny. And that goes by this number of gravitons divided by m Planck square, which is way, way too small for mass system like proton mass. Okay. Now, if you ask the question, and that's the place where Dyson's argument came in, that how large your detector should be to detect even a single graviton, and if you take, let's say, Earth number of protons in the Earth, and let's take the lambda to be the Earth radius, and you ask that. The mean free path length argument that you want to detect at least one graviton, even for Earth size detector, this quantity, if you evaluate, because you know the Earth's density, you can convert that into how many protons Earth has, very rough order of magnitude computation, you find this quantity is way too small. And that was precisely Dyson's argument that it's extremely hard to detect graviton in any laboratory. So the best way to detect graviton would be the indirect. So what is indirect? So essentially, it's a scattering diagram. It's a scattering amplitude you're looking at. You're bringing in two masses. You want to interact them, let them interact sufficiently such that gravity becomes the most important contributor compared to your electromagnetic interactions. So what you're looking at the S matrix phenomena, where you're going from pure to entanglement state or entangled state because of the interaction. So this is the experiment which we have been talking about, and Vlatko's talk was relevant because he also spoke a little bit about the setup. So effectively, from particle theory perspective, you're setting up an S matrix. You have got Alice and you have got Bob, and they are interacting via your the graviton exchange. And in the S matrix, you can look into the final state by the S matrix elements. So essentially, you have embedded a spin, which I think we have spoken about it a couple of times already, like in Year's talk as well, that you're embedding spin, and spin becomes your helicity states or spin states, and you want to understand how the spin states are entangled. So this is like your ruler essentially. So you have there are four possibilities: up, up, down, down, up, down, and down, up combination, and these are your final state. This is the way you create your final state. So once you know your final state, you can actually compute concurrence, which is very similar to entanglement. The concurrence and entanglement entropy, or von Neumann's entanglement entropy, has very similar feature, and you can compute what will happen in the relativistic scattering, what will happen in a non-relativistic scattering. You can compute all these elements because you know effectively all the elements of your S matrix now. And you can compute the concurrence, and especially for the non-relativistic case, you always find that the system can entangle where there is a wide range of scattering angle for which you will get the entanglement. But in experiment, you don't want to use concurrence. You want to use some witness, entanglement witness, which is easier to compute from the experimental perspective. And for the experiment, it's of course a basis dependent quantity. It's not a basis independent. So you look into a particular basis dependent witness, and in this particular basis dependent witness, if this quantity is less than 0, you say that your two systems, whether you call it Alice or Bob or system 1 and system 2, they are essentially getting entangled. And if they are getting entangled, and if there's no other interaction, so this is a big assumption, and that's the place where our game will come in. How do you get rid of those interactions? So if there's no other interaction, then you can ascertain that graviton is quantum in nature. But the problem comes, again, your Feynman diagrams, because any material you pick up, it has some dielectric constant, it has some diamagnetism, it has some paramagnetism, it has all these properties. So just to give you a simple example, like a Casimir interaction. Casimir interaction is a dipole-dipole interaction. electron, positron, they're interacting with your QED. Is a famous QED Feynman diagram which you can construct. And Casimir actually way back in 1930s computed this famous diagram. Of course, actually he used this Feynman approach to compute the diagram, and later on he changed the method. And now there are various ways you can compute this Casimir force through also looking into the virtual photons completely by looking into the vacuum fluctuations. But at the end of the day, the answer remains the same, and this is the answer for a two spherical system if they have the dipole, and that becomes your biggest enemy.
Anupam, you have 5 more minutes for the talk.
Thanks very much. So I think as we highlighted, as some of us have already highlighted, that if you really want the graviton to dominate here, or graviton-induced entanglement to dominate, you really need to take care of the photon-induced entanglement, because photon is also a carrier. If there is a dipole, it will also entangle the two systems. So photon can also entangle and can cause a huge background for us. And this is one of the biggest background. And actually it was Andy who pointed out to us way back in 2017 that one has to be a bit more careful in the experiment. As Sugato pointed out, that the masses which we need in this game is roughly 10⁻⁻11 grams. The superposition which we need is roughly around 100 micron, and the closest separation we need is 200 micron. In order to get the phase which is order 1. Of course, it's a very, very tall order, as we have heard today in the morning, but we have not come anywhere close to that kind of masses we are talking about. Of course, it's for future, but nevertheless, I think the effort, as we have all heard and learned, that we should continue in this direction. The biggest enemy besides this electromagnetic interaction is also decoherence, and that's the place where Jerry's talk comes in. And we were asking this question: how is the level of vacuum which he can reach in a laboratory, because all the decoherence rate is nothing but the scattering rate. Again, it's if you can scatter, you can decohere as well as you can entangle, depending on the language which you're talking about. So you have to make sure that if you want to suppress the decoherence rate, you have to make sure that the scattering rate with other quanta, it could be cosmic rays, it could be photons, it could be fifth force, even hidden axion or hidden photon. You have to shield it from everything. So you have to make sure that the decoherence rate is tiny. I will not talk about the fundamental decoherence rate due to purely gravity. It's way too irrelevant for the purpose, but someone can ask me later on. So just to give you an example, I think Jerry's talk was very, very helpful and very, I was intrigued by the fact that he reached even a much smaller level of vacuum, which he talked about, 10⁻⁻27 or -28 Pascal. But in order to perform this experiment, to avoid any air molecule scattering from photons due to emission and absorption, you need the vacuum to be 10⁻⁻15 Pascal, roughly around temperature 0.1 Kelvin or so. But having said so, there are a number of problems here. I mean, Yar pointed out, so I'm not going to go through all these directions, but one particular way which one can ameliorate at least the QED part is to impose some kind of like a conducting plate. And people like Larry Ford and others have computed this kind of configuration, that what is the Casimir between a sphere and a conducting plate. And so conducting plate will essentially act like a Faraday cage, but gravity cannot be put in a Faraday cage. There's no Faraday cage for gravity. So graviton would still interact between the two system 1 and system 2, but you just ameliorate the Casimir this way to a certain degree. I mean, there are, of course, we have investigated quite a lot of details with this kind of setup, but one of the things which I think is important to mention, that gravity, when you do any experiment with gravity, the gravity becomes your enemy. And that's because of the finite size effect in the sense of equivalence principle. So you have to make sure that you protect your capsule such a way that you're not prone to sudden jerks, sudden seismic noise if a butterfly passes by or if a snake slithers and things like that. So I will not get into the details of any particular, the plot here. You can ask me later on, or maybe Marco will explain a little bit more in this direction. But what I'm telling you is that just to give you some idea, if you want to do this kind of experiment, we need a huge effort from international community, because the best way to perform this kind of experiment would be underground. You have to go something like 50 to 100 meters, and you have to go for a free fall, because here you want to make it as small g as possible. Keep in mind that even in International Space Station, it is 10 raised to minus 3 times g. G is, let's say, 10 meter per second square, so 10 raised to minus 2 meter per second square. But here I have to go to way too low in order to understand, in order to get rid of the gravity gradient noise. So that's one of the reasons. Maybe it's better to go for free fall laboratory in the underground, where you can perform a controlled experiment rather than sending things into the space. Ayer has talked about quite a lot about this, and then very recently we are now trying to design with Sugato and Ron and Ryan will talk about it perhaps tomorrow or day after tomorrow, that how to create massive superposition. And is it at all possible to create superposition with masses roughly 10 raised to minus 14, minus 15 kilogram systems? And there's a huge challenge. I mean, by no means it's a closed topic. There are many challenges, and we need better design, just to highlight. But just to conclude, although I spoke about purely from the gravity perspective, you can, as Sugato pointed out, you can measure gravitational waves. You can talk about dark matter. You can modify your propagator, and you can talk about axion, hidden sector photons. You're checking the foundations of quantum mechanics. You're checking the foundations of gravity. You're checking also very, I would not, maybe it's better, slightly out of outlandish, perhaps, topics such as Penrose's collapse mechanism, where quantum mechanics has to be changed drastically. So there are many things which you can check. It's not just purely gravity. So it's one kind of experiment. If you go for it, then you can do many things from the material science, from cooling, from decoherence, from condensed matter, and quantum foundations of quantum field theory. So it's an amazing avenue for young people. So, but it demands international collaboration. And so that's the reason we are all here today. And thanks a lot for listening. Thanks.
Thanks, Anupam. And let us hear, maybe we have time just for one or two questions. So I see Tejinder's hand up. Yeah, Tejinder, if you would like to.
Yeah, thank you, Anupam. That is a very exciting talk. I actually, on the other hand, I have a slightly different viewpoint. Namely, I'm a little uncomfortable with the assumption that gravitons do exist, and it's now only a matter of detecting them. There is another viewpoint that gravity is actually emergent and only classical. And in the quantum regime, what sits in for gravity is actually something like a quanta of the Lorentz symmetry. You gauge the Lorentz symmetry, and you get spin 1 so-called universally interacting gauge bosons, which mediate what would eventually become gravity. So I was just curious, in your this entanglement of two masses experiment, which I do think is very beautiful. Suppose the mediation is not by gravitons, but by spin 1 so-called Lorentz gauge bosons. Is there some picture how your calculation of predictions might change? I would be interested in something like this.
But Tejinder, as you know very well, that the gravity which you are talking about, even for LIGO, Virgo, or plane wave, is not spin 1; it's a spin 2 quanta. So you need to bring in spin 2 quanta.
No, I have a problem with that. Maybe we talk more in the discussion session.
Slightly out of conventional things.
Yes, yes, we'll talk about it in the discussion. Yes.
So we have time for another quick question if someone wants to ask something. Yeah, Marcus.
Yeah, thanks. Great talk. And of course, it's a very important and big goal to get these supermassive, super widely superposed in parallel superposition, so to say. And the only question to me is, because I didn't do the math for the very massive things. So how are the cross sections growing for neutrino scattering and for certain types of expected dark matter particles? Is that a bigger problem than the vacuum that you were worried about?
No, you are absolutely correct, Marcus, because you have to, that's one of the reason one has to go to underground, because you have problems with cosmic rays, you have problem with the neutrino, and even the neutrino can event can trigger decoherence. So you're absolutely correct. So this is one of the reason, I mean, you know, we were thinking about looking into the kind of like underground, you know, technique. And not only that, maybe I have just for illustration purpose, I have drawn this diagram. At the end of the day, it may require something like a Russian doll, that the baby doll is sitting, you know, so you have to preserve the capsule so well that the way you're performing the experiment is embedded within a capsule, then it is embedded within a capsule. The more capsules you bring in, the better you are shielding your experiment. So yeah, you're absolutely correct. So these experiments will be perhaps the most delicate experiment we could ever perform on Earth. And yeah, so there are humongous challenges. So let's face it, there are many challenges, but you know, that's the nature of mankind, that we want to pervade through all these challenges.
Okay, yeah. So I think we are right on time for the next talk. So yeah, so let us proceed and hear Dan. Yeah, Dan Carney.
Great. Good. So yeah, thanks very much for the invitation to speak here. And I'm going to give a talk that actually really nicely dovetails the previous two talks and discussion. So, you know, I think Vlatko and Anupam really nicely set this up. So they sort of said a lot of what goes into my very first slide. The question I want to ask is literally spoken in the title here. So in a little more detail, the question is the following. So Anupam, you know, thoroughly reviewed the idea that if the graviton does exist, it will generate, you know, in some low energy model, an effective Newtonian potential like we see on Earth, and it will be entangling. So we will see entanglement in these sort of Newtonian entanglement experiments. But I think there's like a deeper question, which is the converse true? So if I see the Newtonian entanglement, do I necessarily know that the graviton is there? And there's been some previous work I'll review. I want to just, in this talk, give a very sober and probably painfully precise analysis of this question. And I'm doing that only to point out that you can, and because doing it precisely, you actually find some counterexamples. So the precise statement is bolded here, you can read it. Basically, I'm going to say that if you see the Newtonian entanglement, and if I further assume Lorentz invariance and unitarity, and maybe I have to assume a kind of notion of causality, then I can conclude that something like the graviton exists. And I'll spell this out as we go. So like I said, there's been some nice previous work in this direction. So there's this really beautiful paper by Alessio Balencia and this group. And what they do is they basically analyze a thought experiment, which is exactly modeled on sort of these experimental proposals where you have an Alice and a Bob. Alice prepares some massive superposition and tries to use it to signal something to Bob faster than light. And they show pretty convincingly, and this is not really new, this is a very long understood problem, if you only had an entangling 1/r interaction, you could do faster than light signaling. So you have to say something else to solve this problem, and they show that if you quantize the metric perturbations, then you can resolve these sort of signaling problems. But the question is still, again, the converse. Is it the only solution? And I'm going to actually show by construction the answer is no. Like I said, this is a very old problem. Actually, Fermi famously in 1932 incorrectly concluded you could signal with a 1/r potential. And this was sorted out over a series of papers by various people. And there's a nice review in this recent Dickinson article. So I'm going to discuss everything in a scattering theory formalism. And there's a reason for that. So since I think there's a lot of sort of foundations oriented people in a workshop like this, I want to say how I think of scattering. This is a sort of modern approach to it. It's really just to prepare and measure black box setup. So in scattering, it just means you can prepare some state, say in the far past, and I'm going to measure some state in the far future. And what I'm doing is basically tomography on some unknown dynamics that happens in the intermediate times. And the only questions I can really concretely ask, observationally, are things like what are correlations in the out state given the in state. So scattering is just an example of this with sort of some further restrictions on what exactly we're doing. And these are the restrictions. So the input and output are specifically taken to be sort of far separated particles, so with reasonably well-defined momenta. And the black box is assumed to be a unitary time evolution. So I assume I prepare some state, it evolves through some unitary that I maybe don't know what it is. And then finally, I measure the outgoing state of some new particles. And the only rules I need to impose here are unitarity. So the S matrix itself is literally just the time evolution operator from past to future infinity. So I'll assume that is literally a unitary operator in the usual sense. And then this is a little more sophisticated, but this is Lorentz invariance is totally standard formulation of this. Just means that these incoming and outgoing states have to transform in unitary representations of the Lorentz group, which really just means they're labeled by momenta, spins, and then maybe some internal quantum numbers that don't transform under the Lorentz group. Furthermore, it means that the S matrix commutes with the Lorentz group elements. So this is actually going to be enough to draw some pretty strong conclusions. The other thing that I have to input is the experimental idea. So experimentally now, the other piece of data I'll have to put in is like, suppose we did an experiment and we saw the Newtonian interaction in generating entanglement and doing everything we think it will do. So I'll spell that out in more detail. The workhorse in the formal argument I'm going to present is unitarity. So unitarity means something quite specific in scattering theory. So I want to go through this. It's very standard. So sorry if this is remedial for many people, but with the weak interaction like gravity, the usual way of doing this is you decompose the S matrix into a term that means no scattering happens and a term T, which means scattering does happen. And overwhelmingly, the probability, the most likely outcome is nothing happens. There's some subtleties with the infrared divergences in a pure gravity model, and I can talk about that later. You can write this down in components where these alpha and beta cats just mean lists of momenta and spins. And you can use this to define these sort of M matrix elements. These are just the matrix elements of the transition operator. Okay. So unitarity in this language is equivalent to what's known as the optical theorem, and this really just is the optical theorem you learn in E&M, just applied to the Schrödinger equation instead of the Maxwell equation. Mathematically, what it says is that the imaginary part of any scattering amplitude has to satisfy some consistency relation with squares of matrix elements, but summed over arbitrary final states X. Okay, so I hope this is very abstract, and I think it'll become clear as we go exactly how this works. But the key, and this is where sort of everything is going to happen, is this is a constraint on sums over all the final states in the processes you have. So what I'm going to make an argument that basically says that the sum on X has to include something like the graviton. Okay, so concretely, I'm going to show some equations next, but before I do, let me tell you the strategy. So I'm going to take experimentally as given. We've, who knows if this is 30 years from now, but we have done one of these experiments. We know the Newton potential is there. We know it's truly a two-body operator. It can entangle things, and I can put it into the Schrödinger equation just like we think we should. Okay, I'll take that as given. Then I'm going to use that to compute a non-relativistic scattering amplitude. Okay. So that's a reliable calculation using just the Schrödinger equation and this Newton potential. And then I'm going to sort of bootstrap this into a relativistically invariant scattering amplitude. So find, the Lorentz invariant extensions of that. And then I'll check the unitarity of this model. And what we'll see is that unitarity cannot be satisfied unless you have processes where radiative bosons, really gravitons, actually fly away from the experiment and exist in the asymptotic Hilbert space. I regulate the Newton potential with a little mass mu, and you should just think of mu as a small parameter that goes to 0. Although I would like to emphasize that all of these proposed experiments happen at length scales that are sort of like micron to maybe a meter. And so actually all you really know, if you're hard-nosed about this, is that mu is, 1 over mu is less than a meter or something. So it's small, but it could be finite. Okay, so with all that sort of preliminaries, here's really the argument. So this will look, like I said, formal and precise because it's important that you can make a formal and precise argument of this form. I'll try to walk you through the intuition as we go. So like I said, I start by computing some scattering matrix elements. So let me just consider the simplest thing, 2 particles. So these can be like the nanospheres in these entanglement experiments. I prepare them in some state. I let them interact. At some point, they are interacting through the Newton potential. Then they fly apart and I look at them. what's the scattering matrix element? Say given 2 incoming momenta to go to 2 outgoing momenta. Okay, so time is going to flow from bottom to top on all these diagrams. The matrix element is just the usual thing. You just compute it in the Born series, chapter 6 of Sakurai or whatever it is. And what you'll find is that the lowest order in the gravitational coupling, the formula is very simple. It's just g Newton times mass squared, that's the coupling strength, divided by the momentum transfer squared. And that's just the usual Rutherford formula that everyone knows and loves for electron-electron scattering with a different coefficient on top. So now I want to bootstrap this, if you will. I want to find a Lorentz invariant version of this. And it's easy to show that, in fact, the only option, given the fact that I have to just use these external momentum values, the only way I can do this is actually take these 3 momentum vectors and make them 4 momentum vectors. So this may look a little subtle if you're not used to thinking about relativistic physics, but in other words, I'm using an IJ indices and I'm putting them into mu nu indices, right? So this is now a Lorentz invariant quantity, and it's the only one that will have a non-relativistic limit given by this top line. This is a little technical, but it will matter in the next slides. This amplitude is completely real in the way I'm organizing this. Okay, so with physical momenta, this numerator, sorry, the denominator is always positive. There's no pole, nothing interesting happens. This is real. And so unitarity in terms of the optical theorem is trivial. The imaginary part of the amplitude is strictly equal to 0. So actually you can't say anything very interesting from here. I'm going to use this notation that I take the Newton potential and I draw it as a sort of line. This little dotted line means this, if you want, propagator. Although at this stage, it has actually no interpretation as a particle. It's just a way of computing the amplitude. So to get something non-trivial, you have to do a slightly more complicated kind of scattering calculation. So this diagram actually should remind you of this Alice-Bob diagram that I showed earlier. So I have 2 parties. So you can think of, say Alice is on the right of these diagrams and Bob is on the left. And you have Bob has a particle and then he like prepares it or releases it or whatever, and some time passes and then Alice measures it, and I'm drawing these little incoming and outgoing photon lines, and that's just an abstraction of the fact that to prepare the particle and to measure the particle, you have to talk to it with some physical system, and unless you're doing something really nice like a QED measurement, you have to change the energy in the intermediate state. So you either put energy in or take it out, for example. Okay, so this now, I don't know how many people have thought about 6-leg Feynman amplitudes, but if you draw this out, if you do the bootstrap just like I showed before, you get this kind of complicated looking diagram with lots of lines. But I label them just for clarity. The real point is that when Bob, say, injects a photon onto his massive object U1, and then this massive object now picks up some light-like momentum, and that has important consequences. So in the 2-to-2 scattering, the momentum transfer, if you want, is purely space-like. It's always a positive squared quantity. Now I can get a light-like momentum transfer basically by imparting enough photon energy in the preparation phase. So what does that mean? So it means that now in the Newton potential term, so that's this middle thing, g Newton over m squared with this k twiddle, this k twiddle can now become negative. K twiddle squared, excuse me, can become negative, and I can have a pole in this amplitude. And on the pole, this I epsilon is going to matter. So just for future reference, this total amplitude scales like the Newton constant, and then times 2 factors lambda. Lambda is just the interaction strength between this photon and this massive particle. Okay, so how do we analyze this? So we have to check unitarity of this amplitude now. So if we look at unitarity, as I was saying, the pole in this middle term suddenly matters. So there's an imaginary pole, so the residue is imaginary. Precisely when this is very abstract, this k twiddle squared becomes equal to negative mu squared. If I'm talking about the strict Newtonian limit, this means when k twiddle squared is just null, it's a light-like vector. So you can sort of start seeing this is going to be the interpretation, is that when the thing becomes an on-shell fluctuation. But to spell that out, what happens? So I have a pole, I have an imaginary part in the scattering amplitude, and importantly, it scales like this sort of photon coupling squared, divided by the Planck mass squared, which is just the Newton constant. So now I check unitarity. Okay, can I satisfy unitarity of this amplitude? And you're going to find that the answer is no. And it's pretty straightforward little combinatorics exercise to draw the diagrams and see this. And the problem is, if again, I'm starting with, I only have massive particles and photons. There is no graviton so far. And if you draw all the possible diagrams, you're not going to be able to find any amplitude that has the right powers of these couplings such that I can satisfy this equation. So this is very bad news, right? This means that your model is not unitary. The S matrix has a probability deficit, if you want. So how do you fix this? Okay, well, the solution is pretty standard. The solution is you didn't include all of the possible outgoing states. And specifically, you can sort of go through this and figure out that the state you didn't include is the state you're looking for. It's this sort of radiated graviton line here. And the reason this is important is because now that the graviton, say, can be radiated, I can draw diagrams where there's a coupling just linear in the Planck mass. So, this is sort of a proof of concept, but this has to hold for all incoming states and all processes and so forth. And it's pretty straightforward to show that the only solution, assuming Lorentz invariance, is that I include these radiative graviton states. Okay? And they're really like the graviton. So they have to have a low mass as mu goes to 0. That's this dotted line. And they have to couple with the strength of the mass of whatever it couples to divided by the Planck mass, or G Newton inverse. Just to hammer this in, there are more processes, more complicated processes where you get the same result by using the same exact logic. You write the non-relativistic process, you bootstrap to the Lorentz thing, you check unitarity, and you find that the only way to have a unitary model is to include outgoing gravitational radiation. So this slide, I don't think I want to go through it in great detail, but just it's a sort of a more striking one. You can imagine, say, anti-particle scattering, and if you don't include gravitational radiation, you'll find a problem, and the problem is obvious. If you have a particle and an antiparticle, they have to be able to annihilate and form gravitons. If you don't include that, you will get a non-unitary model. And this relies on a sort of microcausality condition that I think I'll skip in the interest of time. Okay, so at this stage, what this argument shows you is the following. If I see Newtonian entanglements in an experiment, and if I assume Lorentz invariance and unitarity, and in the precise way I've defined them in this talk, then you can really conclude that there is a massless or very light boson, and it has to couple to the mass of particles. And just again, to summarize the logic, is if you don't include this outgoing radiation, then the wave function after scattering will have the wrong norm. It'll be less than 1. So this is a fundamental problem. So then the last thing I want to just discuss briefly is, okay, you'd like to say that this is the graviton, and I've been saying it, but with quotes. And the reason it's got quotes is because there's more things that can solve this than just the strict graviton. So let me just show that by construction really quick. So it behooves me to tell you how the graviton works, first of all. So the graviton, in the usual meaning of the term, is a spin-2 field. So it's just a metric perturbation h mu nu, and it couples linearly to the stress tensor of the matter. And there's a root G Newton coupling. So it's easy to show in Anupam. Like I said, reviewed this in detail. If you calculate just tree level 2-to-2 scattering with this thing as an intermediary, this little curly line means a real spin-2 graviton, then the amplitude looks exactly like this thing I showed you before, 1 over the momentum transfer square. The difference is it's got this horrible numerator with all these dot products of all these momenta and stuff. And these come from the tensor nature of the interaction. Specifically, they come from a spin sum running over this propagator. Okay, but clearly all these dot products mean the tensor. There's a lot of tensors going into this calculation. So that's horrible, but nicely in the non-relativistic limit, all of this becomes very simple. You just get a power of the mass of these particles. It happens to be the 4th power, just by dimensional analysis. That should be clear. And so if you put that back into this numerator, you find that the non-relativistic limit of this diagram is just Rutherford scattering. It's g Newton m squared over the momentum transfer squared. There's a 1 over m squared factor due to wave functions. Let's not worry about it. So in this precise sense, if you have the graviton, you will get an entangling Newton potential in the low energy limit. So that's not the only model that can do that. So here's just for construction, another very straightforward example. So this would be like a scalar graviton. So this is some scalar field phi, which is the scalar graviton. And the only way I can couple that, or well, the simplest way I can couple that, is to the trace of the stress energy tensor. So you can go through the usual Feynman diagram calculations and you can get an amplitude. And it looks just like the previous one, except with a different numerator. The numerator is a lot simpler, and that's because the tensor structure of this interaction is a lot simpler. However, crucially, if I take the non-relativistic limit, I get the same answer. Still, there's just mass of the fourth on top. And again, the sort of low energy 2-to-2 scattering amplitude looks exactly like Rutherford scattering. So there's no way of distinguishing these two models if all you can see is the Newton potential. I'll just mention, especially since somebody was asking this in the questions previously, there's a ton of other models you can do this with. So you can put spin 1, you can even do higher spins, doesn't matter. Anything bosonic, so integer spin. The odd spins, it's a little confusing because the coupling won't be universally attractive, so you have to sort of violate the equivalence principle in a precise way. We could go into it, but it's a perfectly reasonable way of doing it at the level of this talk. There are composite models, so this would be like, you imagine there's fermions that condense into scalars, so just like, the Cooper pairs in a superconductor, for example, you have electrons, but they condense into spin 0 pairs. So the graviton could be of that form. That's subject to some theoretical constraints that we could discuss, but at the level of this argument, again, it's a perfectly reasonable explanation for the Newton entanglement. And then there's this emergent gravity idea. So, I could go into this at great length, but just to say, if gravity is somehow an emergent force, I think the conclusion from these experiences, that would constrain, if you saw the Newton entanglement, that would constrain the form of the emergent gravity idea. So for example, in string theory or in ADS-CFT, if that's your basis for emergent gravity, that by construction has a massless spin 2 in the asymptotic spectrum. And so by these previous arguments, it will in fact generate the usual Newton potential. However, if you think about like Eric Verlinde's entropic gravity kind of model or something like that, it's not at all obvious that this is going to work. It's not at all obvious that, if I think of gravity as like sound waves in a fluid, that the sound waves will couple coherently to arbitrary sets of masses in precisely the same way that the usual spin 2 graviton would. So, I mean, it would be interesting to construct a clear counterexample where, say, there's an entropic gravity, but it does not couple in the way that a graviton does.
Dan, I forgot to tell you, it was 20 minutes, couple of minutes ago, actually.
Oh, okay. I have one slide, so okay, good. The last thing is, some emergent gravity models, sort of more heuristic ones, you sort of derive a semi-classical looking Einstein equation. So this is G mu nu equals 8 pi T mu nu in expectation value. And I think Jake Taylor, my long-term collaborator, will explain probably in detail why these models would be ruled out if you can have entanglement generation. So just to say, it's constraining on this set of sort of models. Last slide. So, this is a very hard-nosed statement to say, well, how would you know it's spin 2? And Vlatko sort of hinted at this. So, okay, suppose you saw the entanglement, you could just say, well, by Occam's razor, it's this, we all know that LIGO saw tensor waves and the graviton is the metric and blah, blah, blah. Okay. If you're happy with that, that's fine. If you're not happy with that, if you want to be a little more hard-nosed, paranoiac, like I think many of us are, you really should do an experiment to probe the tensor interaction. And so here I'm just sketching a conceptual example of this, where I do a sort of a quantum bending of light. So I take my mass, like these nanospheres, for example, I superpose it in 2 locations, and now instead of putting another mass next to it, I actually use a light beam. So I shoot the light beam that's prepared in, nominally the 0 state. I shoot it past, and the deflection angle of the light due to the gravity of this mass is now conditioned on whether the mass is in the right or the left state. So I get some entangled state schematically of this form. And what's important about this is that it's actually sensitive to the details of the tensor interaction. So Einstein famously got a factor of 2 wrong, taking the Newton limit in the bending of light, way back when. And that factor of 2 is due to the fact that both the H0 and Hij components of the metric are needed to calculate the bending of light. So if you put it in a simple estimate, this is like going to be pretty hard to see. This is the most pessimistic way of stating it. This is the differential bending angle on these 2 paths, and you're going to hit some ridiculously small number that you need the baseline of the Hubble scale to see. Of course, you can do better. You can put many photons and you can put them in a cavity so that they're bouncing around. But okay, I really just put this up as a challenge for someone to think about a way to do this, maybe a little more intelligently. Okay, so I'll just conclude. This is just a review to make sure everybody knows what I said. So if the graviton exists, it can entangle things, great. You'd like to prove the converse. If I observe Newton entanglement, then the graviton exists. So I think this is the strongest thing you're going to be able to really show here, which is a conditional statement. If I see that entanglement, and if I assume unitarity and Lorentz invariance, then the graviton or something like the graviton exists. I want to emphasize that by exists, I don't mean it's a virtual fluctuation. So this is sort of a typical way of thinking about this. Exist means it is like a very physical thing. It can be created, it can fly away from your experiment, it can be entangled with your experiment, it can carry entropy, energy, and so forth. It is really like there. I do want to say, if you really want to be tough, there's also an alternative interpretation, which is you could just have a violation of Lorentz invariance or unitarity. That's an interesting possibility. But it would have to be of a very specific type. So it would be hard probably to make a reasonable model like that. And finally, as I said at the end, if you want to be really sure that you measure the graviton, the spin to massless graviton, you have to do a slightly more refined experiment, or you have to invoke some kind of Occam's razor or other experimental evidence. So that's a nice challenge for the future. And with that, I'd like to finish. Thanks.
Okay. Thanks, Dan. And yeah, I think there are quite a few hands up already. I think Tejinder's hand was the earliest, which was up. So maybe,
yeah, thank you. Yeah, Dan, that's such a beautiful talk, very exciting. So as I said, I have been advocating that despite the fact that we see gravitational waves at LIGO, the fundamental quanta which stand in for gravity are spin 1, what I call Lorentz bosons. I have a theory for it, universally interacting. Lorentz invariance is retained, unitarity is retained. So from your last experimental point of view, do you have some idea what difference would be there, let's say in quantum bending or any other kind of experiment, where one can sort of test whether it is spin 1 or spin 2, and I'll get 2 different experimental results for it?
Yeah, so with a spin 1, okay, so I said it in words here. The thing with a spin 1 mediator is that, and this is a little technical, but I think everybody knows, if you have a spin 1 mediator, you can have positive and negative charges, and like charges will
right.
And you'd want to do something like that. So yeah, that's really the simplest statement.
What would be the difference? Okay, sorry, go on.
No. Anyway, I was just. Yeah, I mean, okay. So I think Anupam raised his hand next.
Yeah. Please go ahead.
Yeah.
So thanks, Dan. So a wonderful advocate of this topic, which is I really enjoyed. So one thing which I think I always tell, because I think you also come from the particle theory community, so you will appreciate that as well. You see that even in the case of Standard Model Higgs, we did not see Higgs directly. We saw the Higgs as an intermediate stage, as a, like you collide proton, you excite the gluons. From the gluons, you excite Higgs, and then Higgs decay into top quark, bottom quark, and that goes into your 2 photons or 4 lepton. So these are the 2 events which LHC had seen at ATLAS and CMS. So nobody had seen Higgs indirectly by reconstructing all the processes. So I guess, I mean, when you mentioned that your very ambitious experiment, I guess it would be very, very hard, and we will come across the same kind of difficulty as what Dyson pointed out. So my best bet to detect gravity or graviton, not gravity, graviton as a quantum entity would be again indirectly almost like the Higgs case.
Yeah, honestly, that's kind of what got me started thinking about this. So indeed, not even just the Higgs, but the quarks and all kinds of
exactly. Absolutely.
You actually see these radiated. You infer them from a sort of tomography in the scattering process, and that's the sort of philosophy here. And in fact, I think though it does hint, so to infer that you have to make this conditional statement. I assume unitarity and Laurent. I have to make some interpretation, and it really tells you why it would be awesome if Dyson was just wrong and you could just direct a click from a graviton. You wouldn't have to say any of this crap. But I doubt that will be possible. So,
no, thanks. Great talk. Really enjoyed it.
Okay, I think we are also exactly in time to start the discussion session.